Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about LiDAR. So let's dive right into it. Now LiDAR is basically radar on fancy lights, which is light detection and ranging. Is exactly like sonar, exactly like radar, only instead of radio we are using light. Now why the heck we want to do that? If radar is a known thing, why the heck create this new thing? Well, problem is physics, meaning frequency. Basically the shorter the frequency you use, the higher the resolution, but shorter the range. Radars are designed for finding things that are far away, for example a plane and things of that nature. For that reason it has to work on long wavelength. Consequence, if your wavelength is this long, you can't detect things that are smaller than this. So fundamentally, it's like wavelength limits your resolution. So if you want to detect a hand, yeah, radar is just gonna penetrate through. And you can see that in your day-to-day life. For example, your Wi-Fi has two modes, 2.5 gigahertz and 5 gigahertz. 2.5 gigahertz goes far, 5 gigahertz does not, even though it's faster. So that's the same fact of physics applies here, that radio waves are good, even shortwave radio waves are kind of good, but they are fundamentally limited by the resolution they can provide because of the laws of physics. You can't breach that. So how do you get even higher basically resolution, quote unquote? You go to super high frequency, for example infrared, ultraviolet. These things are very high frequency compared to radios. Like wavelengths are tiny. Instead of wavelength measuring in meters, it's basically nanometers. So fundamentally very high resolution. So you can scan a hand. So it's a very high resolution. So, and be mindful, why the heck no optical? Again, you do not want to see this happening around. Ultraviolet is kind of expensive and infrared is kind of cheaper option. But again, even infrared is still much higher resolution than any radar. You can get a radar to scan very large area. For example, a mountain, you'll be like, dude, this looks good, but here's the, this is a mountain, that's why it looks good. If you actually scanned any pixel of it, you're like, dude, one pixel is just like nothing. Can you use this for driving? Hell no. For driving, we need something that matches the resolution of these two puppies. So for these two puppies, we need basically light. So light detection and ranging. So what's the logic behind it? Like the science. The science is very old, very simple. Time of flight principle. Nothing more, nothing fancy, that's it. Now what you have is a synced clock. You have an emitter and you have a sensor. Now everything is synced. It has to be synced. These two puppies have to be synced. So emitter emits, it sends a pulse of photon. The photon goes out there, gets hit by things, reflects, come back and detected by the sensor. During this time has passed. Again, light is very fast but not infinitely fast, so it does take some time. Now this synced factor allows you to calculate the time. Basically, oh, I sent the light 1001, 1002, 1003, okay, light came back. Let's say it's 1003. So computer knows this, that there was a time delay. Now using that time delay, dividing the time delay by half, because again you do not want the distance folding here, you want the distance only one way, so you divide it by 2 and voila, because light speed is fixed and within the reason of reasonable limit, it's more than precise enough, you're gonna get a very good distance measurement. Now higher the clock speed, basically how quickly these puppies are synced, the better resolution you're gonna get. Meaning, can you scan something that is like this small versus like fingerprints kind of small? You need very high speed clocks. Again, generally you do not get fingerprint, but you can get where you can move your hands like this and still detect it. It's like, it is a very good achievement of our clocks technology, where it's like, this is awesome. Like, it may look like, oh, car is scanning so many things. Again, further away things are kind of easy to scan. It's just that when you are like very close to each other, like what is the light lag between here and here? And somehow you have to measure it. So this is one of those things. The better the clock, the better the resolution. But again, same thing can work in reverse also. For example, you are putting a LiDAR in a freaking space station or satellites. You do not need super duper hyper high resolution. You can be like, bro, relax, we're good. So that's how you figure those things out. Now be mindful, this is a single dimension technology, meaning this pulse, all it tells you is distance. Now to make that single dimension technology into 3 dimension, you have to do what we call rasterization or scanning. So you allow scanning. Now how do you scan? You basically scan in one dimension like this, then another dimension like this, and collect all the data, go do this 360. Now you have omnivision. Now you see this puppy. All the line you are seeing is basically scanner scanning that area. So scanner is like, okay, this area is, let's say, 1 meter away. You have nothing other than that. It's just like something 1 meter away. Does not mean anything. Move 5 degree, something is 5 meter away. Move somewhere, something is 10 meter away. Now you know there is a distance. Now do this 360 degree around. Do this in multiple plane. Basically, either you can move the mirror or have multiple emitters, depending which is cost effective. And voila, now you have a 360 degree scan, and where you can detect 3 dimensions, even though the technology is single dimension. However, because of the development of the sensor puppies, we can now even detect intensity, meaning this thing sensor is inherently designed to do one thing, tell you the time. Okay, it tells you. But nowadays we have so much good analog to digital converter, such a good sensitive equipments that we can be like, hey, can you tell the intensity? Meaning it sent X. Now you apply what we call inverse square law. You have distance, you feed that distance into inverse square law. That gives you a data that if this was a perfect reflector, you should get this amount of energy out. Now, of course, you will get much lower than that. How much lower? Now that is a very useful data. Using that data, you can figure out, are you reflecting on tarmac, are you reflecting on a reflective paint, or are you reflecting on basically white markers on the road? You can differentiate. That's a modern technology, but it can be done, because instead of going just carrying one dimension, how far something is how reflective something is. And that could be a very good fail-safe layer in an AI, where you could be like, hey, if you think something looks like a road marker, does it have the reflectivity of a road marker? If it does not, maybe it's just road paint. Maybe you should be very cautious. That's a very good fail-safe layer. It's like, you think that's a, let's say, light pole, it will have fundamentally different reflection. If the glass is on top of the red light and all that, it will have fundamentally different smooth reflection. Are you getting that? Is it a true system, or is it a broken system? Again, if you think it's broken, alert the driver. If it's not, use that. Like, that's a very good extra layer of data that you can get nowadays. Basically, it can tell you, like, if you are scanning this side of your hand, it can tell you like where your nails, just on reflectance. So, modern technology. So what are the use of these puppies? Well, we measure distance from center, meaning if I'm standing here, how far is that puppy? How is that? How is this? That's where you use it, meaning from center to everywhere else. It's a very awesome. And it creates what we call 3D point cloud, because again, there is no dimension to it. All it is just one dimension. You are just plotting that dimension in 3 dimensions. You are like, okay, X, Y, like XYZ coordinate, that's the XYZ coordinate, put this distance. XYZ coordinate this, put this distance. That's how you're drawing it. So we call it point cloud data. It's just, at the end of the day, it's just points. Point cloud data. Now, this probably is fast, continuous, and high resolution. Some of the scanning systems are so high resolution, it can detect cracks on the road. Like, they are that high resolution, especially in ultraviolet. Like, it's going to tell you how bad the crack is. So fast, high resolution. It's compulsory for self-driving. Can you do self-driving without it? Short answer, not reliably. Why? Again, why the human eyes make mistake? Again, sometimes we get overwhelmed. Chondiana, it's in Hindi we call it chondiana, as in like, you're going to get dazzled. And you must have seen that Tesla is trying to do this, because again, Tesla is not selling as much as they were planning. And again, majority of their stock value has fallen. And not to mention, people are realizing that Elon Musk is much closer to a scammer than to a savior. So at this point in time, they had to cut the cost. And again, they already cut like $2,000 to $3,000 and euros in models. So how the heck you save money? Remove radar, remove sonar, remove, claim like somehow light is going to solve everything. It's like, our eyes can't do it, which has million years of evolution. Give AI good data, awesome output. Like, we have a saying in computer, garbage in, garbage out. Why the heck you are giving garbage? It's like Lidar is an absolute thing. It tells you, and you must have seen like many times Tesla is like literally went inside a truck. How the heck that happened? Again, the computer got confused. It happens. How the heck a car, literally there is a flattened truck here, and car is like, you know what? This is a good idea. Bam! Person died. It's a real thing. That's why, like, Tesla always says it's level 2, not self-driving, and there are people trying to sue him. And again, legally they should sue him to the ground. It's like, dude, if it's not self-driving, don't call it self-driving. Don't say like self-driving, condition applied. There is no condition applied. That's the whole point of self-driving. So, can you do a quality level 3, level 4, level 5 self-driving with this? No, you have to have LiDAR. That's why I'm saying that. So do not go like, oh, Tesla can do this. No, not reliable enough. Again, even with hundreds of because LiDAR gives you absolute data now, so that's the final layer of check. Whereas like if LiDAR is telling you, it's like, bro, something is there, don't go there. And if camera is saying, I think I can go there, you always prioritize LiDAR data, and LiDAR says, don't go, don't go. So self-driving, remote sensing. For example, this is a very amazing way of scanning riverbeds. Now, why do you want to scan riverbeds? Well, that's how you figure out how the heck the flooding is going to happen. Basically, flooding intensity, flooding is like, you can scan that. Now, how can you scan that? You use green laser. Why? It penetrates very deep. Like if you use any other spectrum, it generally does not go. Thankfully, green does go, so you can scan very deep using green system. Robot sensing, and again, drones, they also use it for farming equipments, meaning they can scan a lot of things and figuring out a lot of intensity data. Robotics, again, warehouse robotics, they are running on it. Your Roomba running on it, literally. So these are the uses. Again, be mindful, if we can ever make this cheap enough, it will be put in things that we never even thought of. It's amazing technology, just that not cost effective. So what are the problems with this puppy? Well, problem is that it has moving parts. Engineering rule number 1, thou shall not have moving parts. Moving parts wear down, they break down. And not to mention, on ideal scenario, this will break down. But if you put something that, high speed motion on something that is itself moving, for example, like a car, even if you're like, oh, it's electric car, far more stable. No, because again, it has to travel on roads. The road have movement. There are shocks have movement. Person inside have movement. All of these things combined make their bearings job far more harder. Over time, it always wear down. So fundamentally, no matter what you do, these things do not have long lifespan, meaning your whole car engine block should have similar kind of lifespan, right? Like you do not expect like, oh, piston head wore out before the engine block did. That should not happen. Like you should have like full lifespan. Everything else is the same. Again, rather than tires and rubbers and like, lubrication oil, you don't change anything other than that. But here it will be like, yeah, every 5,000 kilometers change the lidar. Yeah, the glass is worn down, the bearings are not stable. That's the issue. So cost, size per unit, because it's not a mass production unit. It's more of like engineering tool that somebody figured out, hey, these things are now fast enough that we can put on a car. Other than that, it's like it's an engineering tool. Architects use it. It's kind of amazing tool, but again, not used for this sort of environment. So they Control-C, Control-V it. It does work. It's just like not long lasting. And consequence, it was not designed to be mass produced. It's like, thankfully, camera sensors are mass produced. So we have very cheap camera sensors, but we do not have LiDAR that are cheap enough. And not to mention, moving parts are fundamentally cannot be made cheap enough. Like your hard drive, there will always be X amount of price to it, because again, the amount of thing it has. SSD you can make very cheap because inherently it's just a one PCB with some flash chips. You can make it very cheap. You cannot make hard drives that cheap. Again, moving parts, lifespan limitation. So another aspect of the big and bulky size is that aerodynamic drag. It puts so much aerodynamic drag that if you have the same amount of weight, let's say weight is X, you put the X inside the trunk, the range would be more or less same. You put X on top of the car, range will literally be X minus 10%, X minus 20%. Especially, it will be even worse if you're traveling at high speeds or highway speeds. That's how bad the aerodynamic drag on these puppies are. It's like it's bad. It's like it's bad. You cannot do this in long form electric vehicles. Again, it will waste too much energy. And that's why you will always see this sort of technology plastered on fleet vehicles, meaning those vehicles not supposed to do very long drives, especially not very high speed driving. And in those sort of scenario, again, the cost would be very high. But again, if a fleet autonomous vehicle is working, it should be able to serve more than 5 to 10 customers per day. And over time, it should make you enough revenue that even the cost of that technology is like, it's a minor thing. So what we want is very high performance, meaning it scans everything, it scans it very thoroughly, tells you, dude, this is a lane marker. How can I be damn sure? Because the reflectance is very high. Everything, high performance, everything high. And again, how many dots it's doing, those things will be high. Is reliable. Again, it should have the same reliability as your car computer. It should not be like, oh, these things you have to replace. No, these are expensive things, so they should last. And if that is done, then we'll have growth of self-driving. Right now, can we do self-driving? Do we have the computational horsepower? Easy. Do we have the chassis and the vehicle electronics? Easy. Do we have the LiDARs? Easy. Do we have cheap enough LiDARs? No. That's why we don't have level 5 or level 6. Again, level 5, level 6 have been achieved. Long ago, we have achieved it. It's just that LiDARs are not cheap enough, not robust enough, not reliable enough. You have to have like 2-3 LiDARs, and then you hope that no matter what happens, only one LiDAR fails. If you have like 4 or 5 failing at the same time, the car has to be out of commission. So that's how the problem. Like fundamentally, spinning boy, not a good boy. So what we can expect in the future? Well, we need what we call solid state. True solid state, not DLP. Many of the basically bots that are built for warehouses, they claim they have solid state LiDAR. What they have is a laser firing on a DLP, digital light processor. Now these puppies have tiny mirrors and these mirrors are bouncing, and it's awesome, it works. But again, it's still a moving part, and consequence of that, like, isn't those machines should be reliable? It is, but very high vibration environment of car, even those puppy won't last forever. And not to mention, where do we use DLP? We use DLP in projectors, where we like put it once, forget about it. Not like move it every 24/7 into 365, move it, and they're like, oh, wait a minute, tiny mirrors are falling off of it. Again, tiny things, not built for like robust, got tier 10,000 G performance. It's not built for that. So DLP is a good system again for warehouse robotics. They are flying off shelves. They are low cost effective, efficient. But because again DLP is inherently a sensitive thing, inherently small mirrors, you can't have very high laser power. Consequence of that, outdoor range is very limited. Meaning in indoor 10 meters, 20 meters is more than good enough. Outdoor you need to start at 100. Like I can scan something 100 meters away minimum. So DLP does not scale that well. Can you force it? There are companies that are trying to make bigger mirrors, but again, always pros and cons, same thing. So what we want, a true solid state, meaning we have this and laser goes where I tell it to. Basically like this magic, where you have sensor, emitters so to say, and emitters are sending photon and photons are becoming kamehameha and voila. Now here's the deal, this is real world. Again, it does not look this anime inspired, but it is real world thing. This is what we call phase shift array technology. And if you are familiar with any sort of technology, you know this is a common thing in radios and 5G. It's a common thing. It's just that nobody had figured out till this point how to do this on light spectrum, because be mindful, light wavelengths are tiny. Like each of these pixels have to be tiny to be like very close to each other. Only then they can steer the beam. And God help you, like how the heck they are timing this by. Again, they have phase shifter. Each of the pixel quote unquote has phase shifter. And the calculation, the mathematics is like whole different level. And it actually does this. Like you can have a straight diode and diode will like, nope, yep. It can do that. Now be mindful, there is a very good chance you have the same phase shift technology inside your house. If you have new Wi-Fi routers, many of them have beam forming technology. Same thing. This is what we want. Now, is it here? Yes. Is it here in like mass and high resolution? No. Like this is a good thing. Compared to basically using DLP, this is much better. Now, is it as high power as like, having a mirror? No. Why? Again, this is just a starter technology. Think of this way, it's like a VGA camera sensor. We need 100 megapixel, this is a VGA. As more diodes will be packed together, more control efficiency would be put into there, the better the beam forming would be there, the more things we can do. And this is the final stage we want, where it's like no moving part. It's just a thing, bolted on a thing, the end of the thing. So, and what about detector side? Again, that's the emission side. What about detector? Thankfully, CMOS development, because of the mobile industry, is exponentially improved. So we can do whatever we want, even including the fact that we can now scan, hey, what's the reflectance? Not only you're just getting X value, you are also getting Y value, which feeding to, computer, you can get better results. Why? Better in, better out. Fast processor for crunching data. Again, that problem is also solved. On chip, this is where we are stuck at this point in time. This is not on chip yet, meaning these things are very tedious. Like there are some videos you can watch and it's like very complex robotics that are doing the soldering wire bonding as they call it, very complex. So those things have to be simplified, where it's just on chip. Exactly how we had mobile phone development, meaning back in the days, if you have opened a Nokia phone, you would have noticed it has a separate chip for modem networks. Now it's like all those things went inside a unit. Back in the days, even GPS had its own chip. Now everything is now inside one black box we call system on chip. That's what we want here. There are only three components here. You have processor, you have emitter, and you have receiver. If all these three things can be packaged into one unit, and the closer that unit is, the smaller that unit would be, the better we will off. Now these things are small enough where instead of having that, it's like this big in real world, like this big. You can put it in top of the car, not even top of the car. You can just put in the bonnet area. Engine basically below the headlights. That's the perfect place for it, and it works flawlessly. And you can put 3-4 of them all around, because it does not have the luxury of 360 scanning. The beam can only be focused in a small radar. That's why I said like these pixels are good, not great, not yet. So you do need multiple of them, but thankfully these are small and efficient enough where it can be done. We are just expecting it to become more powerful. So pulse intensity to become faster, and the signaling integrity to become so efficient where scanning is should be even faster. Because be mindful, detector side, we're ready, we're good, we go. If this can be made even better, problem solved. And if all of this can be put into one chip, that's the final goal of photonics. That's where everybody is trying to get. Put everything one chip. If that happens, which again, be mindful, more than enough people, more than enough smart people are working on it, that it could happen. Again, I do not know the time, but I'm very sure it's going to happen. It's going to change the world. Like it's such a subtle thing that you will not notice it, and randomly other things will start to change. Be mindful, we use this technology for everything. We just can't use it as much as we want simply because it's too expensive. And again, cheap self-driving car. We can have self-driving today, but just it's not cheap enough. Instead of costing millions of dollars, it will start to cost thousands of dollars, then every Tom, Dick and Harry will have self-driving car. And this is a technological limitation. It's not the AI, it's this goddamn thing. I really love this animation. Video down below. So this was my presentation on basically Lidar. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.